Yeah, and then the last 20 minutes of class, there'll be a little quiz. So I'll try and leave 15 to 20 minutes for you to take the quiz. It's a shorter quiz, I think. So I think it should go pretty well. Okay, so today, or I should say on Wednesday, we were talking about the null space of a matrix. So that was the space of solutions of the equation AX is equal to 0. Let me just pull this up. So the techniques that we were using to describe the null space of a given matrix. So for given a matrix A, what we did is we reduced it to this new form, reduced row echelon form, where we had a pivot of 1 in as many rows as possible. And anything above that 1, we reduced to 0. So this was the final example we did, where you take a matrix, you reduce it to this like reduced row echelon form. And then from there, you're able to write X and Y, your pivot variables, in terms of these free variables that correspond to the free columns of our matrix. And so how we determine what the null space was going to be is you put it in reduced row echelon form, you write X and Y in terms of the free variables, and then you write out this generic vector and then rewrite it in terms of the free variables. And this gave us a description of the null space. So this is what we did on Wednesday. And today we're doing pretty much the exact same thing, except instead of solving systems of linear equations where B is equal to 0, 0, we're instead going to be looking at arbitrarily B. So we can have numbers like 2 or 3, 8, 5, 6, 7, or something like that. And it's not going to change much, as you would expect. It's just going to make it so like you're still going to have like this null space component, but added to that null space component, you'll have like some constant vector. Okay, so this is what section 3.3 is talking about. The complete solution of AX is equal to B. And so as I've stated a number of times in this class, one of the main goals in linear algebra is to understand the solutions of linear systems. So given like a system of linear equations, we want to solve AX is equal to B. And so we saw on Wednesday that the row reduced echelon form and special solutions lead to a complete description of the null space of A. This is what I've just been talking about. So set of solutions of AX is equal to 0. And so now we want to think about like, what if we have a system of linear equations of the form AX is equal to B, where B is not equal to the 0 vector? And so we're going to suppose that x1 and x2 are distinct solutions of the system of linear equations. And so an interesting thing to note is that if we were to take the difference of the solutions, or the difference of the solutions x1 and x2, and we were to multiply it by A, by linearity, so by distributing multiplication over this difference, we would have ax1 minus ax2. We know this a times x1 is equal to b, and we know a times x2 is equal to b as well from this equation. There's solutions of this equation here. So this gives you b minus b, so this is equal to 0, or the 0 vector. And so what this is telling us is that if you take two solutions and you subtract them from one another, you get a vector that's going to end up being in the null space. So this is really saying that we have that this x1 minus x2 is equal to some vector xn, where this xn is an element in the null space of A. And so what this means is that if you were to add x2 over to the right hand side, you would be able to express x1 as a sum of a solution, so x2 plus some vector in the null space. So from here, we can write x1 is equal to x2 plus some vector inside of the null space. Okay, does this make sense? Like we're writing a solution in terms of another solution plus a vector in the null space based off of this being equal to 0. Any questions about this part? Okay. And so this is going to be, this captures the main idea of this section. So the main idea is the following fact, is if we let A be an m by n matrix and we let B be some vector in Rm, then if we have some solution xp of the system of linear equations given by like ax is equal to b. And we have that any solution of ax is equal to b can be expressed in the following way. So we can write the solution x as being equal to some particular solution plus some vector in your null space. So that's what the second half of this box is telling you. Xn is the vector in the null space. Xp is just some solution. It's not, it says like a particular solution. We'll derive these, what it means to have like a particular solution. So what this is saying is you can write any solution as a solution plus some vector in the null space. And so this should be like maps onto intuition a little bit. In the past, we saw that if we have an empty null space, that means we have either no solutions or a unique solution. And we saw, and so this would correspond to x just being equal to some particular solution, like x would just be equal to xp. We wouldn't have like this x to the n. So we would have a unique solution, or there'd be no solution at all. And we also see that if we have a vector in a null space, so if we have a non-empty null space, the solutions are going to be equal to some particular solution, and then you add to it all the linear combinations of vectors you can have inside of the null space. So that will give you infinitely many solutions. So it should map onto your intuition in terms of the relation between the null space and the number of solutions you have for your system of linear equations. Okay, so it's all kind of abstract right now. So we'll go through probably like 2 examples today. So for this first example, it wants us to find the complete solution of ax is equal to b, where we have A is this 2x4 matrix, and then we have B is this 2x1 matrix. And so to solve this problem, it's pretty much exactly what we were doing on Wednesday when we were trying to describe the null space of a system of linear equations, except now instead of having an augmented matrix with 0, 0 at the end, we're instead going to have a non-zero vector. So we're going to have 3 minus 1. And so if we wanted to solve the system of linear equations, so we're going to put this into reduced row echelon form. So the first thing we can do is we can add, or we can multiply 2 to the first row and add it to the second row. So if you were to do that, you would get 0, 0, 1, 1, 5. And so you can see already we have 2 pivots. And then if we wanted to go to the next step, what we would do is we would want to get rid of this minus 1 that's above. Well, let me circle the pivots just to be clear. So these are our 2 pivots, right? They're the first non-zero entries we have in each row. And so to put this into reduced row echelon form, all we need to do at this point is just add the second row to the first row. This would get rid of this minus 1 that's above this pivot right here. So if we were to do this, the second row remains the exact same. Let me get a little bit more space. Then the first 2 entries stay the exact same. So this will be a 0, and then this will become minus 1. And then we have a 3 plus 5 would give us. Okay, so these are the 2 pivots that we have, this x and this z. So again, I'm going to keep doing this over and over again. Each of these columns correspond to variables. So we have 4 columns, which means we have a system of linear equations and 4 variables. So the first column corresponds to y, second column to, or first column to x, second column to y, third column to z, fourth column to w. And so at this point, we can read off the following system of linear equations. So we have x plus 2y minus w is equal to 8. And then we have that z plus w is equal to 5. And so the y and the w, they don't have pivots in these columns, so these are going to be the free variables. And so we're going to be solving for x and z in terms of y and w, the free variables, just like we were doing on Wednesday when we were solving for the null space. right? So we have x is going to be equal to 8 minus 2y plus w. And then we have that z is going to be equal to 5 minus w. And so everything is pretty much the same as we were doing on Wednesday, except now we have these constants, right? And so we can follow the exact same process we did on Wednesday. I'm gonna make a little bit more space here. So we can follow the exact same process we did on Wednesday. We can write out this generic vector x, y, z, and w. And so we can write everything in terms of y and w, the free variables. So we have x was equal to 8 minus 2y plus w. We had y is just equal to y. Z was equal to 5 minus w. And then w is just equal to w. I'm going to move this down here. And so we can rewrite this now in terms of the following combination of vectors. So there's going to be 3 vectors of interest. There's like this particular solution that was mentioned in the beginning of this section, and then the rest is going to be the null space. So we're going to write out 3 different vectors. Really, we're just decomposing this vector in terms of a linear combination. So think about it like this way, I guess. This first vector is just going to consist of the constant terms inside of this vector right here. So this is going to be 8 in the first component, corresponding to this 8 here. The second component is just going to be a y. So it doesn't have a constant term. So this is just going to be 0. The third component has this 5. And then w doesn't have a constant term, so this will be 0. So this is the particular solution that it mentions in the beginning. So on the second slide that we covered. So this is the XP, i.e. the particular solution. It has nothing to do with the free variables or anything to do with the null space. Right? It doesn't have anything to do with y and w. And then these other 2 vectors are going to be the null space. Right? Because it's linear combinations of the free variables that we have. So the y component in the first part is going to be minus 2. In the second component, we just have y, so that's going to give you a 1. 5 minus w doesn't have a y component, and then w doesn't have anything to do with y. So this will be the vector corresponding to y. It's like just factoring out a y from like the vector here. And then the w, we have a w in the first component, which will give us a 1. The second component is just y, so it will be 0. We have a minus w in the third component, so it'll be a minus 1. And then the last component is just w, so you have a 1. So this is what the complete solution is going to be. It's maybe this is like a little messy, but this is the complete solution. Or what it means when it's asking you to find a complete solution. So, I mean, this is like this whole part came from Wednesday. The only thing that's new is we have like this particular solution in front. And so what this is saying is that any solution to the system of linear equations that was given to us is going to have the form of having the vector 8, 0, 5, 0 plus like some linear combination. So y and w can be any real number, and it'll give you another solution to the system of linear equations. Okay, so before moving on, I just want to make one other observation. So something that's nice about this matrix is that we have a pivot in every single row. And so this is going to have implications. So if we have a pivot in every single row of our matrix, this is going to tell us that we're always going to have at least one solution. Right? We don't have a row of zeros, so there isn't the possibility of having no solutions. So one comment you can make about the system of linear equations is that ax is equal to b and in this case, we have more columns than we do rows, so we have free variables. We're always going to have free variables. So AX is equal to B will have infinitely many solutions for any B. The keyword being like for any. So even if we chose any other vector B, no matter what that vector B is going to be, we're always going to have infinitely many solutions. So like we're never going to have no solutions and we're never going to have a unique solution. Yeah. Sorry.
And that's because there's free variables?
So there's two parts to it. Because we have free variables, it means that we could have infinitely many solutions. So that's one half of it. The other half is because we have a pivot in every single row. So because we never have a row of zeros, we can never have no solution to the system of linear equations. So like no pivots or like a pivot in every row cancels out the opportunity for having no solutions. And the fact that we have free variables means that we have we can't have a unique solution. So that leaves us with the only possibility being we have infinitely many solutions. And this doesn't depend on the vector B at all, is the main point. Okay, any questions about this before moving on? Okay. Yeah, so this is something that can generalize. So we're going to focus on a new definition. So what it means to have full row rank. So if we have that A is an m by n matrix and the rank of A is equal to m, i.e. the number of pivots you have is equal to the number of rows of your matrix, then the row reduced echelon form cannot have a zero row. And so there's 4 things you can determine based off of this information. We have that A has m pivots. This is due to the fact that rank of A is equal to m. We have that AX is equal to B, has a solution for every single B in Rm. We have, because there's m pivots, it means the column space of A is going to be Rm. It's going to be a linear combination of m vectors. Just from the definition of the column space, it's the span of the pivot columns. And then we have that the free columns, the number of free columns you have is going to be the difference between the number of columns you have and the number of rows you have in this situation. So the free columns provide n minus m special solutions of AX is equal to 0. So this is saying we have n minus m free variables. Okay, so this is an important thing to remember for this class. And of course, there's also going to be this notion of a full column rank as well. So I'm going to go through one more example before the quiz. I'm going to go maybe a little bit faster just to make sure you have enough time for the quiz. So for this one, the next one, it wants you to find the complete solution of AX is equal to B, where A is 1, 2, 2, 3, minus 1, 1, and then B is 4, 5, 5. And so if we were to reduce this, we would do minus 2 times row 1 plus row 2. This would end up giving us 0, minus 1, minus 3. And then if you added row 1 to row 2, this would give you 0, 3, 9. So you see the third row and the second row are scalar multiples of one another. So if you did minus 3, or if you did 3 times row 2 and you added it to row 3, it would cancel out row 3. So it would give a row of zeros. And you can also multiply the second row by minus 1 to make sure you have a positive 1 as your pivot. And then to finish off this row reduction, you would want to get rid of this you would want to get rid of the 2 we have up here. So if you were to do that, you'll do minus 2 times row 2 plus row 1 would give you 1, 0, 0, 1. Oops. 0, 3, and then minus 2. And so what this tells us, like this would be the final row reduction, like loose row echelon form. So we have that there are 2 pivots and we have 2 columns as well. So we don't have any free variables. So we have no free variables. And so what this means is that the vector minus 2, 3 is the unique solution. It's gonna be a little bit tricky because it looks like we have like a 3 by 1 vector. But in order to multiply a 3 by 2 vector, And then to get a 3x1 vector, you have to multiply it by a 2x1 vector. So that's why it's like minus 2, 3 and not minus 2, 3, 0. So we have minus 2, 3 as unique solution to the system of linear equations. And I guess one thing worth noting is that AX is equal to B doesn't have a solution. So it does not always have a solution. It does in this case, but it won't always have one. For instance, what if you did like B is equal to like 1, 1, 1 or something like that? If B were equal to 1, 1, 1, you would end up getting a non-zero entry in the third component. So you would have a row of zeros, but then you would also have a non-zero entry here. So you would have no solutions. So this isn't an example of having full column rank or full row rank because we had a row that didn't have a pivot, but it is an example of what's called full column rank. So for every single column of our matrix, we had a corresponding pivot. And so this is going to tell you that if you have full column rank, you're either going to have a unique solution or you're not going to have any solutions. So this is kind of this analogous definition. I want to make sure people can actually copy this down if they, I don't know if I went too fast, but so there's this corresponding notion of having a full column rank. It's not letting me choose. Okay, there we go. So if we have an n by n matrix and we have n pivots, i.e. the rank of A is equal to n, this tells us that there's not going to be any free columns, and thus we're going to have an empty null space. And so there's 4 things we can derive from this. We have A is going to have n pivots. The only solution of AX is equal to 0 is going to be X is equal to 0. So I mean, we have no free variables. We have an empty null space, or the null space only consists of the 0 vector. That's what this is saying. This tells us that the columns of A are independent and span an n-dimensional subspace of Rm. And then if AX equals B has a solution, then it only has one solution due to the fact that we have an empty null space. So that's what you can conclude immediately upon seeing that you have full column rank. Okay. Yeah, so there's one other example. I'm not going to go through it now because I feel like it's more important you have enough time on the quiz, but it's something I want to go over in class on Monday because I think these are important. And I should say, like, just to explicitly say, like, this is the complete solution. Like, even though we just have one solution, this is like the complete solution for the system of linear equations. Okay, any questions about this example? Okay. Okay, quiz time. Let me stop recording 1 second.